time we started to design double reinforced section. Double reinforced section means we have reinforcement, much reinforcement in tension and some reinforcement in compression. This reinforcement in compression will help concrete to support compressive stress. Because we have limitation, we cannot increase our reinforcement for any reason. We have restriction for this thickness, for this total depth. So first situation, we assumed steel reinforcement in compression yields. So we have compressive force in steel reinforcement in compression. We have compressive force in concrete. We have tensile force in steel. If you apply equilibrium equation, summation f of x equals 0, so this force plus this force equal this force. From this equation, T equal C concrete plus C steel. From this equation, remember, I told you I assumed compression steel reinforcement yields. That means stress in this steel reinforcement is yielding stress, F yield. So the only unknown in this equation, A, which is the depth of your compressive stress block, you can get A. Once you get A, I can assume your total cross section with area steel at the bottom, area steel prime at the top, your concrete area can be divided to two parts. The first part, a little bit of your reinforcement, area steel 1 with the concrete cross section. The remaining steel reinforcement, area steel 2 with area steel prime. Remember, area steel 2 and the area steel prime are equal. From this relationship, I can know what is the value of area steel 1. Anyway, your force in area steel 1 and force in concrete can make Mn1, nominal moment for the first part, equal area steel 1 time F yield, which is T, time distance in between. This distance equal depth minus A over 2. Then the second part, we have tension force in this steel reinforcement, compressive force in this steel reinforcement. That means moment or nominal moment coming from the second part, Mn2, equal area steel prime time distance in between, which is equal D minus this little distance D bar. For the total cross section, the final nominal moment equal nominal moment number 1 plus nominal moment number 2. You can add phi for this equation to get your design moment. Phi in this cross section equal 0.9. Remember, before going, you assumed assumption at the beginning. You assumed compression steel reinforcement yields. We need to check if this assumption is correct or not correct. So we have two triangles. I'm looking for this value, which called epsilon steel prime. This value in this little triangle is similar to another triangle, this one. If you make triangle similarity, I can say the highest point, 0.003, which is epsilon concrete ultimate, divided by required value, this one, divide this one, equal this distance, which is C, divided by C minus D bar. The only unknown is your epsilon steel prime. You can find the value. This value must be greater than or equal epsilon yield to make this assumption correct. Epsilon yield equal F yield divided by E steel. E steel, put it in your mind, 29,000 KSI. One more time, for this triangle, we have two triangles. The first one, epsilon Cu equal 0.003, the total depth C. The second triangle, epsilon steel prime, this distance C minus D bar. So this triangle is similar to this one, so I put this relationship. Any question? Today we will talk if epsilon steel prime smaller than epsilon yield. That means, actually, if this happens, we need to repeat all of our calculation. If this that happens, that means compression, steel, does not yield. So what will happen if your compressive or compression steel reinforcement did not yield? The only thing, this value, not F yield, it will be F steel. Just a reminder, your stress-strain relationship for steel reinforcement, something looks like this. If your steel reinforcement yield, that means you are here, F yield. If your steel reinforcement, and this value, epsilon yield. If your steel reinforcement did not or does not yield, that means you are here, or there, or there. Anything in the linear relationship, F steel. What is the value exactly? I don't know. This is a problem. I don't know what is the value of Fs right now. So for this equation, we have two unknowns, F steel and distance A. So your problem becomes more complicated a little bit. Let's see. So to design double reinforced section, we need first to assume. And we hope this assumption is correct because we are done. But if your assumption not correct, we need to do more calculations.
Dr. Ayman, we want it to be in the elastic region of the stress strain.
Not only the whole cross section, but only steel reinforcement and compression, only in elastic region. Okay, but this one yields, this one at ultimate. The only thing is steel reinforcement and compression. That means you have much reinforcement and compression. Okay, nothing will change, nothing, except T, which is tensile force in the bottom reinforcement, will be the same. Area steel time yielding stress equal 0.85 FC prime. This part is the same, A. Do you agree? But I write it in beta 1C. That's fine, no problem. Time B, the total term is C concrete. This part. Everything's the same. Plus C steel at this time equal area steel prime F steel or F steel prime. Doesn't matter. So I cannot say this stress is F yield. No, I cannot because your steel did not yield. Okay, what is the value? We have right now two unknowns. F steel, what is this value? And maybe A or C, whatever. One more thing here. I told you before your E, which is Young's modulus slope of this linear relationship, equal what? Opposite which is F, stress, divided by adjacent, which is epsilon, strain. That's right? If you would like to get stress, equal what? E times epsilon. That's right? That's right? Any stress equal Young's modulus times strain. Can you tell me what is the strain in your compression reinforcement? Yeah, one more time. Do another triangle similarity between the biggest triangle and the smallest one. Remember, right now, I don't know what is the value of C, what is the value of A, because I'm repeating all of my calculations. The previous step is wrong. All of your calculation before is wrong, because you did your calculation based on assumption. Your assumption is incorrect, all of calculation is incorrect. So we are right now starting from scratch. Tell me, 0.003 divide epsilon steel prime equal distance C divide C minus D bar. Do you agree? Between this triangle and this triangle, I would like to get epsilon steel prime in one side and everything on the other side. So I think your value will be C minus D bar divide C times 0.003. Do you agree? Just I got epsilon steel prime in one side and everything on the other side. Okay? I would like to get F steel prime. I told you F any stress equal Young's modulus times strain. Right now I know what is the value of strain equals this value. If you multiply this value time E, which is Young's modulus, you can get your stress. Here is your value for F steel. So F steel equal C minus D bar divide C times 0.003 times ES Young's modulus. Put this value here. Time area steel prime plus this one, remove A and put beta 1C equal area steel F yield, the only unknown in this equation, your value C, distance C. Once you get C, you can get A. Then do the same. For the first part, we have area steel 1 with concrete only. Get MN1. The second bar, we have area steel bar and area steel 2. And get the second nominal moment. But remember, your steel stress Fs prime, not F yield. Then add them together, you can get your final moment. Add phi, you can get your design moment. So everything is the same like the previous one, but the only change, we cannot assume your stress in compression steel equal F yield, but F steel, something here. If you would like to get this value, this stress equals strain times E. E is known, Young's modulus, 29,000. What is the value of epsilon? I can get your strain by triangle similarity for this value. Once you get it, multiply this value by E, you can get your stress. Get this term or this expression and put it here in your equation. Apply your equilibrium equation to get distance C. From C you can get E. Let's do one example. We did this example last time.
Yes.
So we have double reinforced section. The bottom reinforcement 4 bars number 10. Go to your table. What is the area of number 10? Multiply this area by 4. You can get area steel equal 5.06. Your area steel. Compression reinforcement 2 number 7. Go to your table. What is the area of number 7? Multiply it by 2. Your area steel prime equal 1.2 inch square. Before starting, what is the value of your depth? This depth, D.
24.
Any answer?
24.
24, yes. What is the value of D prime?
2.5.
2.5 inch. Before starting, what is the value of B? 14 width of the cross section, 14 inch. Then go ahead. The scenario you will do, assume compression, reinforcement or steel yields. I don't know what will happen. So I will start with the most easy option. Assume compression steel reinforcement yields. So I would like to use this story during your solution. Hey, we have something called neutral axis. This neutral axis has a distance C from the top. We have something called strain distribution. Looks like this. According to ACI, we have here epsilon concrete ultimate strain equal 0.003. In your steel reinforcement in compression, we have epsilon steel prime. Your steel reinforcement in tension, we have something here equal epsilon tension.